Good afternoon, everybody, and I welcome, on behalf of the other coordinators, I welcome all of you to the SMCB seminar series. And those who are new to this seminar series, just for you, a brief introduction. So we have been running this series for about 1.5 years now. It was conceived by Professor Biman Bagchi, and it has been running under his mentorship. And so the objective was to introduce particularly the students, the young students, both undergraduate, postgraduate, and also young researchers, to the new areas of research where statistical mechanics is being applied to solve problems in chemistry and biology. So that was the idea, and so far we have been fortunate to have a lot of students in our audience. So that have been our unique point. And also, so we have been running this for a while, and we had 16 lectures so far, and today is the 17th lecture. And we have a mailing list. In case you'd like to receive future updates about this seminar series, please subscribe to the mailing list. And also we have a YouTube channel where you can watch the earlier lectures, and also today's lecture will be uploaded there. So now it's a pleasure for us to today we have Professor Govardhan Reddy with us as a speaker today. He is an associate professor in solid state and structural chemistry unit in IISc Bangalore. And Govardhan did his master's in chemistry from IIT Bombay in 2001, and he did his PhD from University of Wisconsin-Madison in 2006, and he had a postdoctoral research stint in University of Maryland, I think till 2012, and 2013 onwards he has been in IISc Bangalore. And his general research interest is theoretical and computational modeling of physical, biophysical systems, in particular structural transitions in proteins and so on. And today he's going to talk to us about salt-induced transitions in intrinsically disordered proteins. I guess you are skipping the pH part.
Yeah, I mean, I have a few slides at the end. I can show that.
Sure. Okay, please go ahead. Go ahead. The floor is all yours.
Okay. Good afternoon, everyone. First, let me thank Suman, Rajiv, and Ranjit for giving me this opportunity. And I thank the rest of you for attending the talk on a Saturday afternoon. All right. So yeah, so the talk is about how can we think about these salt effects in IDPs. So I mean, recently IDPs have garnered a lot of interest. So hopefully at the end of the talk, probably I'll give you an idea how you can think about how salt induces these transitions in IDPs and how you can think about it. So most of this work was initiated by my student here in my MIT in his last year of his PhD. So right now he's a postdoctoral fellow with Professor Dave Tirmalai at University of Austin, the University of Texas at Austin. And after that, my other student, Lipika, brilliant, hardworking student, she took over and she got it to some conclusions. And this work is supported by NSM. All right, so the IDPs are intrinsically disordered proteins. You know, it's a sequence of amino acids, right? So compared to globular proteins, which fold into specific three-dimensional structures, these are disordered. That means they don't fold into specific structures most of the time. These are rich in polar and charged residues. Since it's disordered, so you can think of its landscape or as a flat landscape with small hills, so that the IDP can bump through or transverse through these various conformations. So as I said, these are rich in polar and charged residues, right? That means you can easily modulate the conformations of these IDPs using salt, because salt can screen charges and it can do other things. For example, also pH as well. And similarly, temperature and other co-solvents also can play a role here. So by varying some of these external factors, I mean, you can push these IDPs to populate certain conformations, and if those conformations, the concentration of those conformations, or if the population of those conformations exceeds a certain level, then they start to aggregate and they form aggregates, and they're implicated in a large number of neurodegenerative diseases. So So as I said, these IDPs are modulated by one of his chain length. Typically, the ones which we see in experiments most of the time are roughly around 100 and beyond. And the properties, of course, it's a heteropolymer, right? So the IDP is made from 20 amino acids. So the sequence also plays a role in its properties. And the other one is the fraction of charge. So you can have charge residues and amino acids. These are the internal factors. So that means these are intrinsic to the amino acid chain. But as I said, you can modulate the properties using external factors as well, like pH, temperature, salt, and co-solvents. So now, how do we think about these IDPs? So by modulating these external factors, you can push the IDPs to sample some conformations. I'll go into detail about these, but for example, you can make them populate rods or coils or globules, they collapse into globules and so on. So yeah, so the importance of how do we think about these? These are transient structures, right? The conformations keep going. I mean, it keeps changing. It hops from one conformation to the other. So then what is the best way to think of, right? So one of the, so here the ideas from polymer physics are very helpful in trying to understand these IDP properties. But I should warn you in the beginning itself, see, IDPs are not exactly homopolymers, right? So here it's a heteropolymer because it's made from using these 20 amino acids. And compared to the synthetic polymers, the degree of polymerization here, right? As I said, here it's typically you have some between 100 to 200 residues in most of the IDPs which we study. But in synthetic polymers, I mean, you can have the degree of polymerization is typically in thousands. So that is another crucial difference between the two, and we have to keep this in mind always when you're using any idea from polymer physics to understand these IDPs. Right, so that's one thing. So what are the key ideas from polymer physics that we use to understand IDPs? So one important thing is we have to realize that polymers are self-similar. That means that means their properties can replicate at several length scales. For example, here you take a part of the polymer and you zoom in. This looks like your original polymer itself. It's not exactly identical, but on an average, the properties here will be similar to the full polymer. Similarly, you can zoom in and you get another part of the polymer which looks exactly like your whole polymer. So that's one important thing. The other ideas, the other key property which we extensively use is this radius of gyration. This is defined as 1 over n, where n is the degree of polymerization. That means the number of amino acids in the chain. Ri is the position of amino acid I, and this is the center of mass. It typically gives you the size of the IDP in a solvent. All right. So the other one, so there are for any polymer, there are two important length scales. One is called the persistence length, the other is the chain length of the polymer. So the chain, how do we understand the persistence length? So let's say this RS is the contour of your polymer, and the derivative with respect to a position on S gives you the tangent at that point. So the persistence length, which is the LP here, it's basically the distance on the contour where the correlation between the tangents decay. So it's a characteristic length where the tangents at 2 points on the contour of the polymer decay. So this is the tangent at some point, let's say origin, and they say that some distance S, and this is a dot product, and when you take an ensemble average, at a typical length scale of LP, the correlation between these two positions decay. So if the polymer is very rod-like, then if it's a rod, like if you take a pen, it's like a rod, so the tangents are always pointing to the same direction. So they're highly correlated. So when you have rigid polymers, when you call a polymer rigid, when the persistence length to the contour of the polymer is much greater than the one. That means the persistence length is larger than the length of your polymer. Then those polymers are, you call them rigid polymers. So in these polymers, your thermal energy typically is not high enough to induce bends in the polymer. And the other one is when the persistence length is roughly the size of the contour length, we call the semi-flexible polymer. So here some interesting physics comes out because thermal energy is roughly enough to induce some bends and you can see some fluctuations. And the other one is when the persistence length is much smaller than the length of the polymer, these are called flexible polymers. So the other thing is now solvent conditions. So whenever you have a protein, when you add something to it, when you change the temperature or you add salt to it, or you modulate the pH, what you're tuning is the quality of the solvent, the interaction of the solvent with the polymer chain. So here as well, so when you can modulate the solvent quality to the polymer. So as I said, these are self-similar, right? So the size of the polymer scales the degree of polymerization, that is the number of amino acids. So it goes as, when it goes as 0.6, or it's called a good solvent, or when the chain, the polymer chain exhibits this behavior, you can say that it's a self-avoiding walk. It's a random walk, but you don't visit the previous position you have visited. So this happens when the solvent likes the polymer likes the solvent more than its other monomers, all right? And you can change the solvent quality by decreasing the temperature, or if you have a charged polymer in water, you can add an organic solvent to it. So in that case, what you're doing is the monomers will no longer like the solvent more, but the monomer will like the other monomers in this polymer more. So the polymer starts to shrink or compact. So when the Rg goes as n to the power 5 in those conditions, it's called a theta solvent, or it's called a Gaussian chain or an ideal chain. So this happens when your second virial coefficient goes to 0, right? So these are called ideal solvents. So when the polymer really hates the solvent, it collapses into a globule-like thing like this. Then it goes as n to the power 1/3. That's called a poor solvent because the polymer doesn't like the solvent at all. So the globules you see in semi-flexible chains, but if you have in flexible polymers, but when you have semi-flexible polymers and when you go to poor solvent conditions, you see these toroids formation or spindle-like formation. All right. So these are some of the basic things which I will use to analyze the data. All right. So if there are any questions, you're free to interrupt. Yeah. All right, so the next one is this Rg is mainly extracted from the scattering experiments, like the SACs or something. So there's a standard analysis called Vinaya analysis using which you can extract Rg, but that's not it. So this, you can show that this intensity at this scattering vector q, you can show that it goes as q to the power 1 by mu, when mu is your exponent. All right. So depending on the solvent conditions, mu is 0.6 if it's good solvent. If it's theta solvent, it's 0.5. If it's poor solvent, it's 0.33. I did not show, but for a rigid polymer, mu is 1. Okay. So when it's rod-like, the scaling exponent is 1. So now, okay, so this goes as, you can show that IQ goes as q to the power 1 by mu. That means for a globule, mu is 1/3. So IQ goes as q to the power -3. So if I multiply by q squared here, this goes as q to the power -1. For an ideal chain, this mu is 1/2, 1 by 2. So this IQ goes as q to the power -2. When you multiply by q squared, then this goes as q to the power 0. For a real chain, you do the same thing. It goes as q to the power 1/3. This is pretty handy because when you plot q squared by IQ, you get 3 different behaviors, and you can readily identify what kind of behavior the chain is exhibiting. So now if I plot q square IQ as a function of q, it's called a Kratky plot, okay? So q square plotted by IQ as a function of q. Here it's rescaled with the Rg to make them dimensionless, but it's fine. So for the folded chain at large q, it goes as q to the power -1. That at large q, that means this factor should decrease. So that's what we're happening. That's what you're seeing. So for partially folded or ideal conditions, it's more or less constant. Yeah, you see that behavior. For disordered chains, large Q, it should monotonically increase. So that's exactly what you're seeing. So this Kratky plot is, it immediately tells us roughly where, in which solvent condition we are in, and and you can get these from scattering experiments. So I'll use this to use the experimental data from Sachs and the Kratky plots to validate some of the models that we're using. All right, so as I said, again, the IDPs are heavily charged. I mean, most of them, the polar and charged, right? So we have to characterize them further to understand them. So let's say we start with the fraction. If F plus is the fraction of positively charged residues and F minus is the fraction of negatively charged residues. So the IDPs, depending on the charge content, they can classify them as either polyelectrolytes or polyampholytes. Most of the biopolymers, like proteins, are generally polyampholytes. So when do you call them polyelectrolyte and when do you call them a polyampholite? So when the fractions of if F plus and F minus should not be equal to 0, that means the protein should have positive charge or negative charge, and one of the charges should be much more than the other one. So that means F plus minus F minus should not be equal to 0. So either the plus charge or the negative charge is high. So that means the effective charge on the polyelectrolyte is not 0. Then we call them effective charge on the polymer is not 0. Then we classify them as polyelectrolytes. Okay. So some of the IDPs which fall in that class are prothymosine alpha and SIC1. Now, what are polyampholytes? So in polyampholytes, you have both positive charges and negative charges, and they are roughly present in equal number. So the effective charge is close to 0. All right. So those are called polyampholytes. And of course, neutral means you have very few charge residues here and there. All right. So one of the example is nucleoport. So these are the 5 IDPs which we have studied. So 2 of them fall in the polyelectrolyte class, 2 of them fall in the polyampholite class, and 1 is a neutral ID. All right. So since these are charged, as I said, salts play a critical role in charge screening. So salts tune the IDP properties very well. Okay. So yeah, so the different regimes, as I pointed out. So when it is heavily charged of one kind, for example, DNA has negative charges along the backbone, then in very low salt concentrations, this is stretched. It behaves rod-like. The scaling exponent, this Rg to the power nu, it goes as -1, right? So this scaling exponent. So mu is 1 for rod. And when the monomer solvent interactions are favorable, then monomer, it's a self-avoiding walk, mu is 0.6. And monomer solvent roughly equals monomer, you have ideal theta conditions, and it collapses to a globule, then mu is 0.3. Right? Okay, I hope I'm audible.
Yes, you are. You are.
Yeah, okay. Yeah. Right. Okay. So now let's look at some experiments here. There's a salt effect on these are performed. These experiments are from Tom Record's group, and he's from University of Wisconsin-Madison in the chemistry department. So, and this was a student whom I knew, Laurel, working with Tom. So I knew about these experiments when I was there and about to leave and so on. So what you can show, what you're showing here is this data is for this protein called LACDBD, and this is for DNA melting, double-stranded DNA going to 2 single strands. And so this is LACDBD in different salts. As you can see that this guanidinium chloride, so this is delta G between the unfolded and folded state. So the guanidinium chloride destabilizes the folded state. So as you go down, the unfolded state is becoming more stable. But whereas the other salts, so in some of them you keep the anions fixed and change the cations, right? So you can see that they are stabilizing the folded state. So another important thing which you should notice here is at low salt concentrations, the behavior of all the salts is identical. Okay. And only when you increase the concentration range, that's when the specific effect of the salt is coming into picture. Okay. So now this is attributed to the charge screening at low concentrations. People say that the behavior is identical and independent of the salt because it's the charge screening here which is dominating the effect. Whereas as you increase the concentration, now the salt-specific behavior is coming. This is called the Hofmeister effect. Okay, so that is coming into effect here. Similarly, for the double-stranded DNA.
Just to clarify this, so I didn't know about it. So it seems that even for guanidinium chloride up to 2.5 molar, I guess it's still stabilizing, right? So
this one till here, the folded state is stabilized, and then it starts coming down. Right, that's right.
No, it crosses 0 beyond 2 molar, right? So the 0 is the point where it is equally stable, right? Where it is delta 0.
So yeah, I think that's right. Yeah. So as in the initial stages, yeah. So the folded state,
it goes through a maximum. The delta G goes through a maximum, but it becomes 0 beyond 2 molar, I guess.
This is delta G. So 1 second. Yeah, this is log, so it has to be equal. So yeah, so both the folded and unfolded states are, I don't know, maybe then we have to check the temperature. Sorry, I didn't pay attention to the temperature. Maybe I don't know if these are performed at the temperature where both folded and unfolded states are equally stable.
Okay. And so this going through this maximum, is it observed only for guanidinium chloride, or other salts may also go through?
Yeah, you can have other salts, but for these salt, guanidinium chloride is a typical salt which is used to study protein folding. It denatures the proteins very well.
Okay, please go ahead.
Yeah. So I think I don't know. I have to check the temperatures. Probably that's the only way you can keep it 0, the folded and unfolded states. All right. So so that's the important point. So the initial stages is attributed to charge screening. All the salts have typical same effect, and as you increase the concentration, the salt specific behavior is coming into play. So in the next one, so this is another experiment. This is a fret experiment. So that's a fret experiment. So here you are looking at the efficiency, the fret efficiency. So in these experiments, for example, you have this protein, you have a donor and an acceptor. You excite the donor and you measure the efficiency of energy transfer from the donor to the acceptor, right? So the efficiency will be high when these two are close, when the donor and acceptor are close to each other. And the efficiency goes down when the distance between the donor and the acceptor is increasing. So this blue data is for, so the color code determines the data. So the blue is for protemosin, integrase is red. So the red data is for integrase. And this one orange is this cold shock protein. So that's the data. So you can see that urea, it's more or less flat. I mean, the changes are not that much compared to the guanidinium hydrochloride, which is salt. So you can see that protemosin alpha, as I showed you, this is a polyelectrolyte. That means it's charged. So yeah, protemosin alpha is a polyelectrolyte. So what's happening here is so the fret efficiency is increasing in the initial stages. That means the protein is shrinking in size. So what's happening here is at low salt, the charges are not screened, so the protein, the IDP is stretched. As you add salt, the charges are getting screened, so it's getting compact, so the efficiency, the fret efficiency has gone up. But as you increase the concentration of guanidinium, the chain is swelling again. So that is the salt-specific effect, and the fret efficiency is going down. Okay, so yeah, so now what is my goal? So so you don't have suitable models to study the salt effect. Of course, I mean, you can construct all atom models, but it's very hard to construct accurate force fields which satisfy all the concentration ranges and it is suitable for all salts and so on. And so my goal is to build, a simple computational model to understand these experiments, okay? At least reliably, at least qualitatively, can we understand how an IDP behaves when you add a typical salt to it. And my goal always is to build simple models and get away with it. Okay. Yeah, try to learn something from the experiment by using a simple model. So far, for the kind of problems I have looked at, this model at this resolution, where each amino acid is modeled as two peaks, one for the backbone and one for the side chain, was really helpful. I'm talking problems at the level where you want to see some large-scale structural transitions. So these models are quite handy if you want to study those problems. Okay, so this is so we extended a model which we studied extensively, the folding of globular proteins, and we extended it to IDPs actually. So actually, I didn't know that Dave was also working on it. So we were doing the same thing. So these are the two papers which talks about these models. So the basic framework of the model is the same, but the parameters are slightly different in both the models. Okay. So it's very simple model, and you can look up on the paper for the details, but it typically has these bonded interactions and the statistical potential for interactions between the various side chains. And of course, electrostatic side interactions are important. So you have a potential term for taking care of these electrostatic interactions as well. All right. So now, as I said, I want to use a very simple model, okay, where I can get all the relevant conformations. At the same time, I can, take this salt effect into account. And as I said, a simple means I don't want to add water, and I want to bring the salt effect as well onto the protein conformation using a force field effect. Okay, typical like I want to add a term which takes into account the salt effects on the protein. So now, how do I take that into effect? Take that into these accounts. So there's a model called the molecular transfer model again, which is very helpful. So I extended this model to salts as well. So I just tell you the basic framework. It has approximations involved. Of course, nothing is accurate, but it's reasonable. It works reasonably well. All right. So in a solution, what do you have? You have a protein, which P stands for the protein, S stands for the solvent here. Don't confuse it with the salt. And we have the denaturant or the salt. Okay, let's take the denaturant. So you have these three components in the solution. You have this term determines interactions of the protein atoms. This is just between the solvent atoms. This is just between the denaturant atoms. And this is protein solvent interaction. This is protein denaturant interaction. And this is a denaturant solvent interaction. Okay. So if you assume that this can be a reasonable energy function for your protein or a biomolecule, so you want to get the partition function, of course, by integrating these terms. So you start by integrating the denaturant terms. Once you do that, you can write it like that. Okay, so there's a free energy because of integrating of the denaturant term. You can further expand this into a protein term, the effect of denaturant on the protein, effect of denaturant on the solvent, and the coupling term, and you can integrate out the solvents also. Then in that case, you can write it as a protein term, the effect of the protein on the solvent, and of course, then there's a solvent term on the protein. You have a coupling term in the framework. We have ignored it. You can, of course, the denaturant also affects the solvent conformation, right? So that term doesn't show up because I've ignored here, but the way I take the data, that also is accounted. I'll show you how. So now what I assume is, so this is the protein solvent interactions. So I need the other term, the effect of the denaturant on the protein. So that is given by this molecular transfer model. So what that this is due to this get transfer. So what he measured is, so basically you want the free energy of transferring a protein conformation from water to a salt or a denaturant solution. And he made the approximation that the free energy of transfer is nothing but the free energy of transferring all these individual amino acids in that particular conformation. So So you have N amino acids. So the free energy of transferring a protein conformation from water to salt solution is sum of the free energies of transferring all these amino acids from water to salt. So each amino acid you further split into backbone and side chain. And the backbone is given by the free energy of transferring that backbone per unit surface area multiplied by a scaled surface area of backbone. So your conformation effect is coming here because in all the conformations, the surface area exposed to the solution is different, right? So that's where your conformation effects are coming. Similarly, you have the side chain here. So this is the free energy of transferring the side chain, that particular side chain K from water to a salt solution of certain concentration C. And this is the surface area of the side chain exposed to the solvent. Now, where do you get these terms? So those are the ones which I knew were available in literature from this Tom Records group at Madison. So these are the two papers where they were which measured these energies for all the amino acids, and that was published. So we exploited that data. All right. So now this is the term without the denaturant, and that's the protein, the effect of the denaturant on the protein. Okay. So you can run a simulation using the full Hamiltonian and get the effect of the salt on the protein. All right. So the details you can just look up the paper. So now, okay, so it looks like a very simple model. Now, why should you believe that it might work? So, of course, so that's where we compute some properties from the experiments and compare with simulations and experiments. So this is where the Kratky plot is a reasonably rigorous evaluation whether your model is working or not. So for all this is using the same parameters for all the 5 IDPs. Okay, nucleoporin, ERMTDN, integrase, and SIG1. So you can see that this is a pretty good. These dots are from experiments, and the lines are the simulation data. So you can see that the model reasonably captures the Kratky plots from the SATS experiments. And this is the RG from the simulations, and this is the RG extracted from the experiments. You can see that this is a reasonable agreement there as well. So what we can say from here is, so the scattering experiments, low Q gives you the large globular size effects, and the large Q gives you the structural details at smaller length scales. Since we reasonably capture the whole range, so we could argue that the IDP, the model can capture the overall IDP dimensions as well as the structure at smaller length scales. So now let's look at how all the 5 IDPs behavior at physiological salt. So this is physiological salt is just 150 millimolar salt. Okay. So we plotted this structure factor scaled with n to the power 3/5 roughly. So that these IDPs have different sizes. So with the scaling, you can capture all of them on a similar plot. So you can see that all of them collapse, and all of them gives you the exponent mu is equal to 1/6. All right. So all of them are behaving like a self-avoiding walk at physiological salt, irrespective of their charges and so on. So now let's understand what is the effect of the charges and what is the effect of when does the salt specific effect come into play. So here we are plotting RG for, I'm showing data for just one of the IDPs. This is SIG1. Okay. So I'm plotting RG as a function of this guanidinium hydrochloride, and this red squares are simulated using just the protein solvent functions, energy terms. There is no denaturant in the picture here when I simulate this. So SIG1 is a polyelectrolyte, I think. So as soon as you start adding salt, because of the charge screening, the size decreases. But after that, that's it. There's no other effect. That effect goes down with like 0.5 molar salt. That's it. The screening effects are gone after that. So there's a reasonably decrease in, I mean, there's like 2-3 angstroms difference, but after that, there's nothing there. But now you add the other term, the salt specific term. Once you add it, you can see that it shrinks in size. But then after that, once you start adding more volume, it starts swelling up. Okay. So this charge screening effect is for just literally disappears between 0 to 0.5 molar. And after that, it's the salt specific effects which dominate in the IDP behavior. All right. So any questions? Okay, so I hope I'm audible.
Yes, yes. I don't see any question in the chat box. I am monitoring the chat box. If there is any question, I'll let you know. Yeah.
All right. Okay, so now, all right, so we can extract these mu's, right? Now, but the point is, can this mu describe these IDP conformations? As I told you that these are, you have to always remember, these are heteropolymer, right? It's not a homopolymer. So we monitored this deviation of, this is a measure to see how the IDP conformations are compared to a homopolymer, which behaves like a sulfur volume bond. So one way to do it is the deviation of the interchain residue distance from ideal behavior. Ideal behavior is Gaussian chain. So the distance between residues I and J will go as L minus J L square. L is the bond length, okay? So that is the ideal behavior, and this is what you observe in your real simulation. That's the distance square in your real simulation. And the ratio you're using that, if it's 1, then it's behaving like an ideal chain, or if it's not equal to 1, then it's deviating from ideal behavior. So you can see that although both of them exhibit the same exponent mu is equal to 3/5, which is the good solvent behavior, you can see that the deviations are completely off. They behave very different from one another because prothymosine alpha is highly charged in the middle. All right, so these are, you can use, so the point I want to make is you can use them as thumb rules, okay, but it doesn't guarantee that the chain is behaving exactly like what this exponent is telling you. So because of the heterogeneity, these are heterogeneous chains, so the ensemble can be highly heterogeneous.
Govardhan, can I ask one question?
Yeah,
yeah, actually, obviously the nu which you have measured, of course, is it gives you the RG scaling, right? So it gives you the conformation swelling and the compactness, right?
But overall dimensions, it doesn't.
Yeah, overall dimension, but yeah, but what about the secondary structure? The like in the ensemble, that how different secondary transient secondary structures are populated depending on the salt concentrations. How do I measure? You know, because IDP also having very highly transient secondary structures, right? Because that also will actually kind of the aggregations depending on the transient secondary structures and their populations, right? So if I understand it correctly, that's also very critical, isn't it?
It's true, but as I said, I mean, so here we are mostly probing how the global dimensions change, not these transient local structures. So this model is not really that good to answer that kind of questions.
Okay, thanks, both. Thanks.
That is one thing, but at the end, I will show you that it might not be that bad. You can capture that as well. I mean, some local transient structures. I can show you that.
Thank you.
So, okay, so yeah, so we have to always remember that. So now let's look at this prothymosine alpha, which is a model for polyelectrolyte, and ERM-TADN, which is a polyampholyte. Okay, so prothymosine alpha is the negative charge residues are greater than the positive charge residue. So the sequence is effectively has a negative charge. But polyampholyte ERM-TDN has the effective charge is 0 because roughly equal number of positive and negative charges. Right. So now once we start adding these three, so we monitored the effect of three salts, guanidinium hydrochloride, potassium chloride, and potassium glutamate. As you can see that in this low concentration regime up to 0.5, they come down, the behavior is same. But once as the concentration increases, so you can see huge decrease in the size. So this is like 55 and this is around 35. So roughly 20 angstrom compaction because of the charge screening. And after that, the guanidinium chloride starts to swell the chain. Potassium chloride more or less has no effect after that, whereas potassium glutamate starts to compact the chain further. All right. So this is from prothymosine alpha. But if you look at the polyampholite, where you have roughly equal number of positive and negative charges. So in the initial stages, when you add the salt, here there's a, instead of here you see compaction, but here you see swelling of the chain. So why do you see swelling? So polyampholytes have equal number of positive and negative charges, right? So there are attractions between these residues. And what you're doing by adding the salt is you're screening out those attractive interactions. Because of that, the chain initially swells. So it increases in size when you add the salt. Now, after that, then again, the salt specific effect takes into account. So potassium glutamate like compacts it pretty drastically. So from 35, it just goes to around 20. So it's like a 15-degree compaction as you add the salt. Potassium guanidinium hydrochloride swells it again, and KCl has roughly no effect, I would say. So yeah, it clearly shows that the model clearly shows that the electrostatic effects dominate at low salt, and at high salt, the salt specific effects are coming into play. Now let's see, are there any like these structural transitions like what we see in polymers as we change the solvent conditions? So that we infer from these structure factors. So now first we look at prothymosine alpha. So in low salt, which is 0.01 molar, which is this red curve, okay? So the scaling, so SQ goes SQ to the power 1/3. So Q to the power -1 means the scaling exponent nu is 1. That means in low salt and guanidinium chloride, prothymosine alpha is behaving like a rod. It is stretched because of the charges, it is stiff. So it's behaving like a rod. So once we add more salt to it, then the charges are screened, then it's going from a rod-like behavior to a self-avoiding walk. That means it's seeing the solvent as it if it's a good solvent. All right. So, but that's what we see in guanidinium chloride till 8 molar. So you just see the transition from rod to a self-avoiding walk in guanidinium hydrochloride. Now in KCl as well, you go from to 8 molar, you just see the same behavior. It starts just behaving like a self-avoiding walk, nothing. But we have seen that potassium glutamate is the salt which tries to compact these IDPs severely. So for potassium glutamate, yeah, you can see that it starts to approach the ideal behavior. That means your second virial coefficient is going to 0. It's behaving from it's going from a self-avoiding walk to a normal random walk. So like ideal or a Gaussian chain. All right. So with increasing potassium glutamate, prothymosine alpha undergoes transition from rod to coil, the self-avoiding walk, and then to an ideal chain. Now let's look at this. So this is a polyelectrolyte. Now if you look at a polyampholite, MTN, so initially in low concentrations, it is already exhibiting like ideal chain behavior. Why? Because it has both opposite charges, plus and minus. So there's good, favorable attractive interactions between the oppositely charged beads. So it's showing in low salt, it's showing a Gaussian behavior. Ideal behavior. Now, once you start adding salt, these attractive interactions are screened out and the chain swells out. So here it goes from an ideal to a self-avoiding walk, which is the opposite of what you're seeing in other cases. And then once you add the salt like potassium glutamate, which compacts it heavily, then it starts going back to again ideal to a swollen globule. So here, what is interesting here is we see an exponent for potassium glutamate in 8 molar. You see this exponent 2/5, which is not the scaling exponent we should observe, because the only exponents you should observe is 1 for the rod-like chain, 1/2 for your ideal chain, 3/5 for a self-avoiding walk, and 1/3 when it collapses to a globule. So you can see this 2/5. So we are curious then, why are we observing this 2/5? All right. So then if you go and it's because we attribute it to the finite size effect. As I said, this polymers, when you're using polymer theory, you have to always keep in mind the degree of polymerization you assume n, which is infinity in most of the theory. But here, these are like 70, 80 residue length chains. So you can see the distribution. The Rg is a function in 6 molar. You see that it still exhibits conformations where the size is pretty big. Now we artificially extended the simulations to 8 molar and 10 molar. I'm sure that you cannot use 10 molar. I mean, you cannot dissolve 10 molar potassium glutamate or 8 molar. But we just perform the simulations actually to see what happens, just to understand whether it compacts. So yeah, with 10 molar, it does go to Q to the power 1/3. That means it's compacting. What this tells us is the crossover region from this coil to globule transition is broad in these finite size systems. Okay, so we have to be very careful in inferring what is happening in these systems by using polymer theory. That's one thing I just want to highlight. So there's a gradual transition, but there's a crossover. It's not very sharp, the coil to globule transition. If you look at nucleoporin is uncharged polymer and you're adding salt. So mind you, there are no charge screening because it's an uncharged polymer. So whatever it is because of purely the Hofmeister effect or the salt specific effect you'll see in these systems. So you can see that in nucleoporin, when you add potassium glutamate, it just compacts and goes to a globule, where you see Q is equal to 1/3 behavior. So it undergoes a transition from sulfur-avoiding walk to a globule. So now this is interesting because now there are results where they link the single chain behavior, and there's a correlation between the single chain behavior and whether the chain exhibits or goes to exhibit this liquid-liquid phase separation and becomes a membraneless organelle or aggregates. So people have shown that if you can force the chain to go lower than the exhibit ideal chain-like conditions, then under those conditions, then the chains can aggregate, either exhibit liquid-liquid phase separation or become aggregates. So that means then these results are interesting. So based on the single chain behavior, you can play with different kinds of salts. And using a particular salt, if you can force it to achieve theta-like conditions, then there is possibility that using that salt under that conditions, and when you have a IDP melt, and if the concentration is high enough, and if the concentration is in the semi-dilute range, then they can exhibit aggregation or exhibit liquid-liquid phase separation. So based on that, so now we constructed this phase diagram where you can see these polymer aggregates. All right. So you have a polyampholyte. So polyampholyte in the low salt region, when the concentration is in the semi-dilute region, that means you have multiple chains, and the concentration is so high that the chains are interacting with one another. So that's the semi-dilute regime. So in the semi-dilute regime, the polyampholytes can exhibit in the semi-dilute regime, and in the low salt regime, they can exhibit this IDP interactions, and they can undergo these aggregation. Why? Because they have opposite charges, and because of these opposite charges, you can induce this liquid-liquid phase separation or aggregation kind of behavior. You can do that for polyelectrolytes as well, but for polyelectrolytes, you have to add these strands of negatively charged DNA or RNA to induce the aggregation in the low salt regime. Now, once in the intermediate salt regime, these will never aggregate because the charges are screened out, which favor the aggregation. So you will not see that in this regime. But in the high salt regime, like potassium glutamate or so on, where you force the chain to achieve theta-like conditions, you will again see the polyelectrolyte, polyampholyte, or the uncharged chains. They can exhibit again IDP condensation because you have achieved these conditions. So here it's purely electrostatic effect. Here is the salt specific effect. And intermediate region, you will not see the behavior at all. All right. Okay, so this is about the salt effects. So I have a few more slides. So we have a couple of minutes.
Yeah, maybe 5-6 minutes you can take. Yeah.
All right. Okay, so we pushed it to study the pH effects, the same model. So as you can see, we sort of use the two extremes. The one is 2.5 and the other is 7.5. So these models are good at studying these extremes as well, because at pH 2.5, the pH is so low that most of your acidic residues can be protonated. And here in this regime, they can be deprotonated. Maybe like 95% of the time they're protonated here, and 95% of the time they're deprotonated. And so prothymosine alpha, what people have shown is, as you decrease the pH, that means in the acidic conditions, it undergoes aggregation. So we just wanted to see what kind of structural transitions you observe when you go from pH 7.5 to 2.5, and we want to, after that, we want to speculate why it aggregates. Okay, so that was the one. That's what we were interested in. Again, we just want to validate the model, right? So luckily, you have the SACS data, and we can plot. So we use the Kratky plot to validate it. So at these two extreme conditions, at acidic pH 2.5 and the 7.5, which is close to neutral condition, we get a good, reasonable agreement saying that, okay, I can sort of trust the model and believe what conformation gets thrown out. Okay, so now what we show here is in this prothymosine alpha, it has three regions. Or at least we divided it into three regions. One is the N-terminal region, and there's the in the intermediate region, which is rich in glutamic acid residues, right? And there's a C-terminal region. So when you switch from 7.5 to 2.5, the RG in the C-terminal region and the N-terminal region is almost the same. There's no change in the compound. Whatever is happening in this intermediate region, which is rich in glutamic acid residues. So what is happening here is, so this region is extended at neutral pH because it is rich in glutamic acid residues. At low pH, all the residues, the glutamic acid residues are protonated, and you're undergoing compaction here. So that is what we see, the change in size. So this E region acts as an aggregation prone region, and the conformations with high beta sheet cannot. So you can predict now. There's a, I get what the, okay, so based on the backbone conformation, you can predict what kind of secondary structure the protein can exhibit. So we sort of predicted what is the percentage of beta sheet region in the whole sequence at low pH and high pH. So at the C terminal and the N terminal, with the pH changes, there's no difference at all. But whatever difference you're seeing, it's in the intermediate region, which is undergoing compaction. So when you switch from pH 2.5 to when it at 7.5, there's nothing, the beta sheet content is absolutely zero in this intermediate region. But when you go to a lower pH, when it starts undergoing compaction because of protonation of glutamic acid residue, those backbone conformations are more favorable to form beta sheet content. All right. So we hypothesized that, okay, so these conformations, whatever you sample at 2.5 should aggregate pretty fast, at least the initial aggregation. So we sort of validated with dimer simulations. So we picked conformations that, at acidic pH and neutral pH, and we started running dimer simulations to see what are the timescales at which it aggregates. As you can see, these N-star conformations at pH 2.5, we call these N-star are aggregation conformation. The dimeration is pretty fast in like 2 microseconds. So I'm showing just 3 representative trajectories, but we have like more than 50 for each case. So it readily forms these dimer kind of simulations, at least showing that the initial oligomerization is pretty fast. Whereas in these other, at pH 2.5, when you start from non-star or non-aggregation prone conformations, on the same time scales, the aggregations are not that favorable. The oligomerization is pretty slow. At some point, it starts going to form dimers, but we have seen that in that case, the intermediate E region adopts these beta sheet kind of conformations. That means these non-N-star states first go to the N-star conformations, which favor aggregation, and then you see the aggregation. Okay, so just let me start here. Let me conclude this here. Okay, so the proposed CGPID model yeah, it can predict IDP properties in salt solutions. So yeah, you can do monomer simulations and try to predict in different salts and try to predict whether they can exhibit condensation or not. And by forcing whether the single chain approaches the theta behavior or not. So in low ionic strength solutions, yeah, charge screening plays a dominant role. And, yes, and here you can use appropriate polymer theories to understand IDP behavior. So if your IDP falls in a polyelectrolyte class, then you can use polyelectrolyte theory to understand how the IDP can behave in low ionic strength solutions. Or if it behaves in the amphylite class, then you have to use an amphylite theory. You can use polyamphylite theory to understand IDP behavior in that region. But in high ionic strength solutions, yeah, it depends on the sequence and the salt identity. So here you definitely need some kind of simulation, or like what we did. Then we can see the transition, whether it's going from a rod-like to a self-avoiding wall, then an ideal or a collapsed globule, or on the verge of collapsing into a globule. Okay, yeah, and this is the last point which I've already mentioned. The simulation methodology can probably be used to predict when salt can induce a phase transition in semi-dilute solutions of IDPs based on the single chain behavior. Yeah, okay, with that, I thank you. Thank you for listening to me on Saturday afternoon. Yeah, if there are any questions, I'd be happy to answer.
Let us all thank Govardhan for a really fascinating talk. So now the floor is open for questions, and already I see a few questions in the chat box. So I'll read them out. But of course, if you want to ask the question yourself directly, please raise your hand and go ahead. And so meanwhile, I'll just go through these questions. So Milan Hajra asks, I would like to know, at high salt, do you say the phase separation is mediated by entropy? So at high salt, should charged polymers show a LCST just like hydrophobic sequences?
Okay, so we cannot predict all those things. So what I'm saying that at high, when you force it to undergo, there's no way I can say all those things. What I'm saying is, when a high salt with an appropriate salt, if you can force it to go beyond the theta-like conditions, that means below the theta, it's like verge on collapsing to a globule. That means it likes other monomers more than your solvent. So that's when it's ideal for it to precipitate out or do whatever. So that's what I'm saying. So those are the conditions where you see these phase separation kind of behaviors, right? So that you can predict. I don't know about whether there's low critical point or phase separation and all those things. So that's the only thing I'm saying, because there are already multiple experiments and computations which show that there's a correlation between single chain behavior, whether it's approaching theta conditions, and whether it can exhibit phase separation. So that's the only thing I want to say. Yeah.
So there is a technical question. What software do you use in your simulation? Do you use LAMPS?
So for these, we wrote our own codes, but you can use technically OpenMM. You can stitch the codes because these are simple functions which are already available in OpenMM. So you can write a Python wrapper and use OpenMM to use. I'm sure you can use LAMPS as well, but I've not used LAMPS. But my students nowadays using OpenMM to do it. So yeah, if anyone is interested, you can write to me. We can help you write the code. So that's not an issue.
So here since a technical question, I'll insert one of my questions here. So how do you evaluate the forces? So I understand from the transfer free energies you get the energetics, but you need to run the dynamic simulation. Is it straightforward to get the analytical derivatives for those?
Right. Yeah, you can actually. So even for the solvent accessibles, okay, for Lennard-Jones and all, you know that derivatives exist.
Yes, right. I'm talking about the monomer solvent interaction term.
Right. Yeah. Right. So the monomer, the denaturant term, right, which is a multi-body term coming from the solvent accessible surface area.
Yeah.
For that also, you have you can have a function. So you can look at the reference. We give the reference what we have used for the solvent accessible surface area. So that is an approximate estimate the solvent area, and it is and the derivative is also very simple. You can just do it.
That will be useful. I'll get the reference from you later.
Yeah. It's an algorithm by Wodak and Janin from PNAS. It's 80s or 90s paper. So yeah.
Next, Shumon Dash asks, is there any amino acid specific effect at very high salt concentration for SiC1?
Is there any amino acid specific effect? So
maybe the sequence dependence or something. I don't exactly.
Yes, if I may. Sorry.
Sure, go ahead, please.
Yeah, so what exactly happens at very high salt concentration for SiC1, that your Rg increases rapidly?
Okay, I'm just trying to see if I show any SiC1 data here. Okay, I did not show it because I think it's very similar to the prothymosine data. So that's the reason why I did not show any of the SiC1. So SiC1 is also polyelectrolyte, right?
It's weak polyelectrolyte.
Yeah. So then what we see is very similar to prothymosine alpha. That's why I did not show that data. But if you have anything very specific, yeah, you can write to me. We can analyze and get back to you if you're really interested in knowing something about it. But regarding the transitions in the ensemble, in the conformational ensemble, yeah, it's very specific.
Okay, thank you.
Okay, next question is from Brotin Dash. Brotin, if you want to ask this, if you can go ahead directly because it's a long question. Otherwise,
hello,
yeah.
Am I audible, sir?
Yes.
So, sir, in low salt concentration, other salts are going and binding to the opposite charged amino acids, and which decreases the intra-protein interaction. That is why the folding is less. Is it due to that, sir?
No. So there is no salt explicitly in the simulation, right? So we are just using only the Debye-Huckel screen potential to take the salt effects into it. There's only screening till certain level. As I show you also, that also disappears after 0.1, 0.2 molar or something. Yeah. So you have that screening effect till 0.5 molar. Then after that, that effect is minimal. The screening or charge effect is minimal.
Okay.
Okay. So now we have two raised hands. First, Rajesh Professor Rajesh Murarka.
Yeah. Govardhan, I think partially Brotin has asked my question, but I think that as you mentioned that you have not introduced any explicit ions here, right? There's it's in terms of Debye-Huckel screening and all these things you have incorporated. But then I was wondering that for potassium chloride and potassium glutamate, if you see that the cations are same actually, but due to the differences in anion character of the anion, obviously the charge density is also different for chloride and glutamate, right?
Generally the anions which play a havoc because the cations, for example, the 2+ ions, so they interact with the solvation shell most of the time. So among the cations is the sodium and potassium, which can use water and interact directly in some cases. But it's mostly these large anions like which can be polarized. Those are the ones which play a very big role in conformation, like glutamates and all those things. So that's what I have learned. But as you can see, I just use an effective potential derived from the experiments, right? So that way, as I said, it includes this solvent denaturant correlations as well, because it's one number which takes into account all those effects, and since it comes from an experiment, assuming that the experiment is done reasonably well, that number captures all the effects.
So is there any way that we can say that, okay, why glutamate is because of the only charge density means it's more polarizable, that's why it is behaving so differently compared to your potassium chloride, or any other specific interactions are due to that it is behaving this, although it in both polyelectrolyte or polyampholyte, both are behaving in a very different manner, right? For potassium.
Yeah. So, but one thing you can tell is if one or two specific interactions dominate, right? Like what you're saying. Let's say that an ion, right, bridges two parts of a protein, making a loop or something. extra.
Right.
But in those cases, and if that population is significant, right? Significant in the sense that, yeah, so the probabilities change and you have to accurately account for that to compute any thermodynamic property. In those cases, your average properties you compute like the Kratky plot and all, there might be reasonable deviations in those cases.
Okay.
Right. So in some cases, that's why we try to first measure something and convince ourselves that that is not the case.
Okay.
For example, in pH, right, I just talked about only the extreme conditions, 2.5 and 7.5. But you might ask me, there are experiments at the intermediate pH as well. Of course, there are experiments, but this model will not work because at intermediate pH, right? So the probability that your glutamic acid is protonated might be 50% or 60%. So I cannot really take out the charge or add the charge. Then I have to do a stochastic simulation where I have to introduce the charge, remove the charge stochastically, and then run the simulation, right?
Right.
You understand what I'm saying?
Right. I got it.
Yeah,
Got it.
so
got
then, yeah, so then see, those effects are hard to account for. I mean, you can do it, but you have to take that precisely into account. So if I don't do that and I compute my Kratky plots for pH 4 or something, they believe they don't reasonably agree well with each other.
Okay. Thanks, Govardhan. Thanks. Nice talk. Very nice talk. Excellent talk.
Okay, next, Parvati, Professor Parvati Vishwas.
So I just want to ask that I know that prothymosin alpha is a highly charged protein, and you have also shown that it has excess of negative charge. So really, does it behave like a self-avoiding rock or more like a rigid rod? And my second question is, what is the physical significance of this scaling regime Q raised to the power -2/5? I think it should be not 5, but yeah.
Right. Yes. So yeah, this is prothymosine. As I said, in low salt, it behaves like a rod. It's Q to the power -1. Okay. Once you start adding salt because of charge screening, then it goes to self-avoiding rock.
Okay.
And and it just stays there for all the other salts except for potassium glutamate, which favors highly compact conformations.
Yes.
And for potassium glutamate, it goes to ideal chain kind of behavior.
And what is the significance of this scaling regime Q raised to
Yeah,
power?
at 2.5 doesn't make sense. So that's why I was showing you this. I mean, yeah, so I'm arguing that it's a finite chain effect, and the crossover is broad here. It's not sharp because in polymers you assume that your n is infinity whenever you do any theory, but here it's like 80 or something. So that's why I'm showing you there's a gradual crossover here. So you can show that in fact from polymer theory that the crossover region goes as n to the power -n½ or something. So the broadness of that region. So at least in this case, I'm attributing to the chain effect, the length.
Finite chain then. And you take only one chain of this prothymosin or a single chain, right? Then how does semi-dilute solution conditions come into play?
No. Okay, yeah. So these are all dilute simulations, but there are experiments and there's multiple people have shown that there's a correlation between when a single chain approaches theta-like conditions.
Yes.
Those conditions, when your concentration is in the semi-dilute range, then the chain can undergo a phase separation.
Okay.
Okay, so using that, I am arguing that now you can use this framework at least to predict whether it will, if you can push a single chain to theta-like conditions. Under those conditions, if you have a semi-dilute concentration, it might undergo phase separation. That's all I'm saying. I'm just using what others have shown and saying that that is an advantage which you can exploit using this model.
Okay, so you don't explicitly introduce any concentration terms here.
No, this is not. No, there's no concentration. There's all dilute simulations. Yeah.
Thank you very much.
Thank you. Is there any other question?
Yeah, can I ask a question?
Please go ahead. Yeah.
Govardhan, we are working on a problem which is partly motivated by the work of Rohit Pappu and Eugenie Shakanovich
Okay.
of liquid-liquid phase transition. I'm also communicating with Parvati in these things. So in those cases, the mechanism of liquid-liquid transition essentially is this, this eLife, the article of Shakanovich in eLife magazine. I never knew that there's a magazine like that exists.
Okay.
But that's a very famous article in liquid-liquid phase transition in polymers involving, and these organelles and the membraneless, same language. Of clearly the same language, but there are very different aspects are being studied by people. Now, what we have done is that we have, I think Songita is here, Songita is doing, another person is doing. So we were putting some linkage, essentially partly started from the one that we are doing, the dimerization thing that we are doing with Parvati. Now, then there is essential an entropy cost. If you form a link and go on forming links and enthalpy ultimately win over A, and you do find a kind of a low density, a high density region. Now, in your case, you are saying, of course, that in some concentration regime, there are these single chain problem. You do have certain linkage forming, right?
Right. Yeah. Okay.
If so, my question is that, my question is that do you see explicit linkage between different parts of the chain, like we see in protein, say ribonuclease? There, of course, it's sulfide bond. And if so, in ribozyme, of course, you cannot break the disulfide bond. But in this kind of cases that people are talking, you can break that bond as a result of entropy. So how much, my question is a little bit, how much of this really have been studied from an entropic point of view? Because this droplet formation, if happens, some kind of critical nucleus does happen in liquid phase transition, there's an enormous amount of entropy cost.
Yeah, right.
So, we find that entropy cost, even in a one like Kratky model or random walk, self-avoiding random walk. So, so I would like to really, I'll talk with you, if I can get hold of you, of course.
So I know liquid phase separation is very popular and it's very crowded. That's why I deliberately avoided that, working in that area. But
there's nobody has done.
No, with the salt, I knew that it is a problem which nobody addressed it, and it is very important for LLPS. So that's
absolutely.
So that's the only reason why I found a niche where I can contribute. So I did that. Right.
That, of course, pH dependence and A dependence. When people did the single molecule spectroscopy, Sunny and other people, they all did ion, salt, and pH dependence, of the protein moving along DNA. That is a absolutely bona fide and a good way to go the problem. So I'm not questioning that. I'm asking I'm picking your brain.
No, so the single chain interactions can happen in polyamphiolites, but other things, they are not that strong, because in polyamphilite, as you can see here, it has both positive and negative charges in the same chain, right? So the single chain interactions, I mean, I remember you asking me whether they can form strong linkages in the chain itself. That can happen in polyamphiolites, in low salt regimes. That's why you see that phase separation in polyamphiolites in low. But if you have polyelectrolytes, you have to add other external chains like RNA and DNA, as far as I know.
So the models, the models that Eugenie Shakanovich and Rohit Pappu talking, they are talking of the linkages and liquid phase transition, the droplet formation. So they then are doing a kind of, they are also talking of IDP. So then they are with IDP with charges, and then the bond they are talking of, is link they are talking of, are probably electrostatic.
Yeah, I mean, if you have to avoid entropy, at least in the low salt regime, yeah, if you have charged chains, it's dominated by electrostatics, right? So,
Right. Yeah. No, but entropy, in my model till now, entropy is mostly conformational entropy. And if I try to have only one single link, then the entropy will blow it away.
yeah.
Okay. But I like beta sheet. You know, if you try to have one beta sheet, you find most of them in protein beta sheet is 3, 4, you know, most of the time 4 hydrogen bonding in the backbone. You try to form one, it will be immediately break, and that breaks because of entropy.
Okay.
So that is the kind of thing that we are trying to develop now in this thing. I'll talk with you, you know, and I'll show you some simulations also.
Yeah, sure. I mean, now with this one, I'm also slowly picking some part of that thing, and we have slowly started something. We can talk with maybe on Tuesday or something if you are.
Tuesday or Wednesday. Okay.
So now
Okay, I'm done.
Yeah, sure. Okay.
Thank you very much. You know, I'm very happy that you are working on this problem, so I can talk with you and bug you.
Okay, so there is another question, Milan. Milan, you can go ahead.
Okay, so Reddy sir, I want to ask something about the explicit counter ions in prothymosin alpha. Prothymosin alpha is negatively charged protein. So I believe that if you have a Debye-Huckel potential, which is a continuum model kind of thing, so if you have a more counter ions, realistic counter ions, the short range interactions of the counter ions will be much more higher than the near about the Debye-Huckel interaction. So I believe that it can drastically change the scenario if you have real counter ions simulation. What is your take on that?
Right, I agree. Actually, we have started doing, at least we want to. So one of the questions from one of the reviewers was, there could be correlations or attractions between the chain because of these ion correlations. That's what in polymers you can show that. So one of the reviewers pointed out that, okay, that is lacking. What is, maybe that can also change qualitatively the behavior. So to address some of these things, we are adding some explicit counter ions just to see that what is the effect of all these things. So right now I cannot really comment on it. Maybe in another 2-3 months I'll have some data to do that.
Okay, so we worked in a problem about the prothymosin alpha and histone that are binding together, and we found that the counter ion entropy plays a very high role in the stability of the two proteins.
I agree. I'm sure it does, because I'm from polyelectrolytes itself. I know that it has a very big effect. The counter ions leaving the chain has a drastic effect. The entropy gained by these counter ions in the solution has a lot of dramatic effects on the chain conformations and what it does. So I'm not doubting you at all. I'm sure that is the case. So yeah, so right now with this model, I cannot say how much it does, but yeah, so right now we're trying to add the explicit counter ions and see how the properties change. Yeah, so maybe in another couple of months, I might have some ideas on, I mean, I can tell you what we find. So as I said, one of the reviewers bugged me about these correlations, the salt-induced attractions between different parts of the chain because of the correlations induced by the counter ions or the salt ions. So yeah, this model will, of course, without explicit counter ions, I cannot answer that. So yeah, so maybe in another few months, I can just let you know what we find from this.
Thank you.
Okay, maybe I'll ask a quick question, couple of. So one thing is, it's a more technical question that you've talked about formation of beta sheets, but I guess you have a course and we don't have explicit hydrogen bonding, right? So how do you quantify beta sheet there?
Hydrogen bonding between beads or what?
Yeah, I mean, so how do you, first of all, how do you define beta sheet? Is it in terms of just the phi angles or?
No, this is just from the, we used a machine learning technique which was published recently. which just based on the backbone orientation, it predicts whether it can form a beta sheet or alpha sheet. And it is shown that it is very reliable compared to your DSSP algorithms and so on.
I didn't know.
So from this, all we get is the backbone orientations of backbone conformations. So with the decrease in the stiffness, okay, what happens when the glutamate is protonated? Then it becomes flexible, right? So that flexibility itself, when we feed it, those orientations itself are more favorable to induce beta sheet-like structures. That's what it shows.
And the other question was, since you are taking these experimental transfer free energy values, are those at a specific concentration, or do you
No, they measure at a range of concentrations.
Okay. And so use those parameters to get your concentration dependence?
So generally for these small concentration ranges, for example, from let's say 1 to 5 or something, the delta G as a function of the salt concentration, it looks linear. So what they publish is the slope for that line and the intercept. So with that intercept, you can interpolate all the delta G's for all kinds of concentrations.
And those are for individual amino acids or for a peptide?
For individual amino acids, yeah.
But that would extend even for a chain, I guess. That, I mean, since your model seems to be working, so I guess peptide chain doesn't make a difference.
That is a standard question. See, the free energy of an amino acid, the free energy of transferring amino acid from water to a denatured solution is not necessarily the same when it has a neighbor to it.
Yeah.
So now it becomes a conditional that something exists to it. But for
but
this,
there could be experimental data. There could be experimental data for small, let's say dipeptide, tripeptide also. I mean, then one can correlate whether, I mean, how much is the dilution?
So yeah, that's what I was trying to tell you. So there was a group in Germany which showed that for the residue level, once you add up, there are reasonable approximations. So
yeah, that makes sense. Yeah. So, yeah, thank you. So is there any other question or comment? If not, let us thank Govardhan for a fascinating talk, and also we had a lot of discussion. And I thank all of you for staying till the end on a Saturday afternoon. And very soon we'll make an announcement for the next lecture in this series, which will happen next month sometime. Please watch out for that for the announcement. And I thank you all of you again. Thanks, Govardhan.
Yeah, thank you for coming.
We'll meet in person sometime soon.
Sure, yeah, bye.
Okay. Take care. Take care. Okay. Bye. Bye, everybody.
Bye bye.